Hello, this is Jack Jackson. Let's take a look at a couple more examples of finding volumes by slicing using integrals, where we've got cross sections which are some simple kind of a shape. In this video, we're going to do a couple of examples where the cross sections are triangles. So here's an example for you. I want you to try exercise. Find and illustrate the volume of a solid with a base in the xy plane bounded by y equals x squared plus 1, y equals the opposite of x squared, x equals -1, and x equals 2, where the cross sections parallel to the y-axis and perpendicular xy plane, in other words, slices for a constant x or parallel to the yz plane, are equilateral triangles where the base of the triangle is in the xy plane. Find the exact value in fractional and decimal form. And here is an activity that you can use to get the 3D version, solids with various cross sections for this GeoGebra activity. So see if you can work this one out yourself and then come back and check your answer against the solution here once you've done it. If you've done the previous exercises in the last couple of videos, then this is kind of just a variation on the theme. So hopefully you'll be able to do this. Press pause now. Okay, in this particular application, this activity, we actually see the Riemann sums illustrated. So we see this thing sliced up into subpieces, and we're approximating the volume by these little triangular prisms. Here it is with 8, 16, and 50 different pieces. So here's the app. Actually, you can do equilateral triangles, isosceles, right triangles, squares, regular pentagons, and semicircles with this, slicing it up here. You can enter a formula for the upper curve, x squared plus 1. So let's see, that's this one right here. So this is the positive part of the y-axis. This is the positive part of the x-axis. And this is the bottom curve, which is the opposite of x squared here. So down in the xy plane, you can see the base there going from x equals -1 to x equals 2. And then above that, we have little triangular prisms. And so there it is with 8. Let's do it with, let's say 20. And it may take it just a second to render here, but there now we have 20 pieces. You can kind of see what they look like. You can see that they're all equilateral triangles when you look at it from that side. And you can kind of look at it from around here and get an idea of what that looks like. Okay, let's give it some more. Let's give it a whole bunch. How about 40? Give it a chance to figure this out and render this for us. Okay, there it is with 40. And see, notice again, they're all equilateral triangles there. There's the base. Looking at it from above here, this is sort of a normal orientation here. And then we have this. Looks like the top of our triangles are actually getting cut off there a little bit. It's going a little bit out of the window. There we go. Now I can see the, zooming in a little bit there, I can see the top of it there. And if I do this a whole bunch, let's see, maybe 100 here, it'll start to look like the actual shape. So you can see the limit process going on here as we apply these Riemann sums. Slices our little volumes of prisms, and now we get a shape there. Yeah, it's starting to look pretty much like the actual shape now with that many. So that's the volume that we're looking for, is something that looks kind of like that. Okay. So with that in mind, let's take a look, go back here. And once again, here's the base down in the xy plane. Here is x squared plus 1 from -1 to 2. And here is minus x squared from -1 to 2. And the region in between is the solid flat base. So notice again these pictures up here. that the base here was just a flat piece, okay, which is this is a shape. And you take a particular slice here, and this is a really, really thin slice of one of these pieces up here. This is the base of an equilateral triangle, and above that. So this base from A to B is this base A to B on an equilateral triangle. Let me remind you about an equilateral triangle. The sides are all the same length. The angles are all the same, pi over 3 or 60 degrees. If you slice it right down the middle from this point to the midpoint, it turns out to be an altitude, so it has a right angle there. It turns out to be a median because it's going to the midpoint. It also turns out to be an angle bisector because of all the symmetry that's involved in this particular figure. So this is 30 degrees, or pi over 6. This is 60 degrees, pi over 3. This is 90 degrees, pi over 2. And we have sides of length s for the big triangle. Well, this makes this little piece from here to here s over 2. And by the Pythagorean theorem, with this side s and this s over 2, this turns out to be square root of 3 over 2 times s. So this is a standard triangle, 30 degree, 60 degree, 90 degree triangle, or pi over 6, pi over 3, pi over 2 triangle. And they have sides of the ratio, well, some length here, twice the length here, and square root of 3 times the length here. And so this gives us the height or altitude of that triangle times the base times a half will give its area. So the base is s, the height is square root of 3 over 2s, and then multiply that by half, we get square root of 3 over 4s squared is a formula for the area of an equilateral triangle. And of course, multiply that area by a thickness, and we've got a volume of one of these little prisms right here. All right. So the length across the base here is the length here, which is this curve minus that curve. So we want to take the top curve, x squared plus 1, minus the bottom curve, negative x squared, and then that's our s. So then we need to square that and multiply by square root of 3 over 4, multiply by dx to get the area, delta x to get the area of one of these guys. Take the limit as n approaches infinity and delta x approaches 0, and this becomes this integral where the delta x becomes the dx, and we're integrating from negative 1 to 2. These two negatives cancel. It gives us x squared plus x squared is 2x squared, and so there's a nice way to look at it right there. Square that out. You square the first term, that's 4x to the fourth. Square the last term, that's 1. Multiply and double for the middle term to be positive 4x squared. Now, that's just a polynomial expanded out, so it's pretty easy to find an antiderivative now. We just add 1 to the power and divide by the new power. So this is x to the 5th, divide by 5, that's 4/5. This is x to the 3rd, divide by 3, that's 4/3 there. And of course that 1 constant just picks up a 1 times the x there, picks up the x. And so we just want to evaluate that from negative 1 to 2. Notice I factored out the square root of 3 over 4 out front. So that's out front the whole thing, so we need a bracket there. And parentheses minus parentheses. First parentheses is this with the 2 in place of all the x's here, here, and here. Same thing here, but the 2 is replaced by negative 1. All right, let's see what we can do here. 2 to the 5th is 32 times 4 is 128, and that's over 5. 2 to the 3rd is 8 times 4 is 32, and that's over 3. Then we got 2. Okay, got 5. 6 negatives makes a positive. That's just 4/5. 3, 4 negatives makes a positive. That's 4/3. And 1, 2 negatives makes a positive, and that's 1. Let's see, 2 plus 1 is 3. 4/5 plus 128/5 is 132/5. 32/3 plus 4/3 is 36/3. 36/3 is just 9. No, 36/3 is just 12. And 12 plus 3 is 15. Now I need to get a common denominator to put these two together. Of 5, so multiply top and bottom of 15 over 1 by 5, that's 75/5. Add that to that, that's 207/5. And then not going to be any canceling here, so you just multiply the 4 times 5 is 20 in the bottom, and 207 times square root of 3 in the top. So our exact answer is 207 square root of 3 over 20, which you can see is what I got here on the calculator, and I let the calculator approximate that for me at 17.92672585383. So that's a approximation and a exact value. I think I said find the exact value and a decimal approximation is what I should say. We can't get the decimal. We can't get an exact decimal. Okay, so there's an example. Let's try another example. So that example, we had equilateral triangles for the cross sections. Okay. Here's another activity that's put together that can do illustrate these kinds of things when the cross sections are isosceles triangles. So here's another example. And let's see, what did I do? I used the same. Looks like I used the same function again. No, this is a different function. Let me fix that for you. Okay, now I've got it how I want it. The function this time is y equals x to the 2/3, y equals negative x to the 1/2, the opposite of x to the 1/2. X equals -1, and x, no, I want to go from, let's go from 0 to 1 this time. X goes from 0 to 1, okay? And the cross sections parallel to the y-axis, perpendicular xy plane, are right isosceles triangles where the base of the triangle is in the xy plane and the right angle is going to be on the lower curve. Find the exact value in fractional and decimal form for this one. And again, you can use this activity here to get the 3D version of the graph. So see if you could do that one yourself and come back and check your work in here in just a second. Press pause now. Okay, well, if you're back, this is what things look like here. The top curve is x to the 2/3 from 0 to 1. That's the green part here at the top. The bottom curve is x to the negative x to the 1/2. Down here is where we're going to have the right angle. And so the triangle is going to be, this is the base of the triangle. And the right here at A, you're going to have the side coming directly up at you with a right angle right at A. And then the hypotenuse is going to come from some place above A back down to this point down here. And here's the 3D version. So like this is your point A, this is your point, say B, if this is B over here. And directly above A, with the right angle here at A, is the top of the surface, and then the side of the surface comes down there. So you got, that looks like that. Okay. And so, well, what do we get? Well, if it's a right isosceles triangle, it's 1/2 base times height. The base and the height are both given by this length here. This length here is x to the 2/3 minus a negative x to the 1/2. In other words, it's x to the 2/3 plus x to the 1/2. We want to take that and square it because the base and the height are the same. That's, in other words, both this length and this length are the same. And then, 1/2 times base times height is the area there. And so that gives you the integral, gives you the volume that we want to get. Let me look here. Yeah, here it is right here. And you can see those cross sections are right triangles there. Let's see if I can move it around. You can kind of see, now you can kind of see those right triangles a little better, getting smaller that way and bigger as we come to the front. So all those are right triangles. If you look at, this side is going to curve around like that. This side's going to curve around. So as this is moving, those are coming around that way. If you look at it from, that's either from above or below there, you can see the strip moving there. That's kind of like what we saw before. So let me get this thing to rotate back around. So anyway, you can kind of see what that thing can looks like from different angles. And you can see what that looks like. Okay. So let's figure out what that area is, that volume is. Here the calculator tells us it's 337 over 364, and there's a decimal approximation, and that's what I got here when I did it by hand. Remember, the area is 1/2 side square, so it's 1/2 that amount squared. Square the first, that's x to the 4/3. Square the last, that's just x. And you double the product. So 2 times x to the 2/3 times x to the 1/2. Now right here, when you multiply these two things, you're adding the exponents, which you have to get a common denominator of 6. So this is 4/6 plus 3/6 is 7/6. Okay, now it's just a sum of power functions, so easy antiderivative. Add 1 to the power, divide by the new power, or multiply by the reciprocal of the new power. So 4/3 plus 1, that's 4/3 plus 3/3 is 7/3, so you multiply 3/7 times 1 for the coefficient of 3/7. Here we have 7/6, we add 1, that's 7/6 plus 6/6 is 13/6, multiplied by 6/13 times 2 is 12/13. And then this one just goes 1 plus 1 is 2, divided by 2 is 1/2 of the coefficient. Notice I had just factored the 1/2 out front, so I need the brackets here. Evaluate from 0 to 1, 1/2 bracket, parentheses minus parentheses. First parentheses is this formula with 1 place of the x's. Second one is the original formula, but with zeros in place of the x's. All of these are zeros over here, so that's kind of convenient. And the 1 to whatever power is just 1, so we really just end with these fractions, 3/7 plus 12/13 plus 1/2. Now we need to get a common denominator here, which is 2 times 7 times 13. So this one needs to be, take that 3, multiply by the 2 and the 13 to get 78. For the 12, we need to multiply by the 2 and the 7 to get 168. And the 1, we need to multiply by the 7 and the 13 to get 91. Add the numerators, that's 337. That's not going to, 2, 7, or 13 don't cancel with that. So multiply the bottom, 2 times 2 times 7 times 13 is 364. And so the final answer is 337 over 364. And I think that this has a 6-digit repeating pattern in the decimal, 0.92582417 with the 582417 repeating. I think that is correct. It's certainly at least the right approximation if it's not exactly correct. Okay. So hopefully that gives you some practice and examples for looking at problems of these types where the cross sections are some known value.